Okay, let's go for it. Find the volume of the solid formed by revolving the region bounded by the curves about the indicated axis. Let's do the first few of these. Here we go. I'm just going to say find the volume. And part A, we're looking at y equals 4x, y equals 0, x equals 2, revolved about the x-axis. Okay, what I'll encourage you to do, just like in the last section, graph. We want to start by graphing just our two-dimensional region. That we do need to graph. So we're going to plot all of this. We're going to figure out what the region is. This one, not too bad, right? We've got this line y equals 4x, so that fairly steep slope passes through the origin. Okay. Y equals 0 is the x-axis. And x equals 2, maybe put a vertical line out here somewhere. There's x equals 2. Okay, so let's first think, what region are they talking about? And well, they're talking about this triangle that touches each of our boundaries. Okay, looks good. And it's revolved about the x-axis. So think about that triangle spinning. I just like to kind of indicate the three-dimensional effect. You know, it's spinning around the x-axis. So this is going to spin around and, you know, it's kind of going to look, I guess it'll look like a cone sort of on its side after it spins around where, you know, the pointed top part is up there and it's got this, it'll have this circular bottom to it on the right side. Anyway, it's not so important. It's good if you can visualize it like that, but probably not absolutely critical. Okay, anyway. First thing to ask ourselves, is this a disk method? When you picture that thing, maybe it is necessary to picture it. Is it a disk method or is it a washer method? So as this spins around, does it leave a gap in the middle or is it solid all the way through? Well, because the region is bordering our axis all the way across, it's going to be solid all the way through. So this is going to be a disk. So for a disk, we know we're using the simpler version where it's just got the one radius. Okay, so what is that radius going to be? That's like, you know, if we can figure out what the radius is and then what the A and the B are, I mean, that's everything. And we've got it set up. Let's see. Going back to the region, I'm going to draw what that radius would look like. Here's how you do it. To draw the radius, you begin on the axis. So if I'm revolving about the x-axis, somewhere in the region, maybe make a point on the axis itself. Then draw a line perpendicular to the axis going across your region and hitting the outer edge. This right here is r of x, that distance. Right? Again, start on your axis and then go perpendicular away from it, right? If it's spinning around, then that cross section would be right there. If it's spinning around the x-axis. Okay. So once we have that drawn, what would r of x equal? So r of x, it's going to be a function in terms of x. Turns out here, that distance is simply our function y equals 4x. If we're on the x-axis and we're thinking, what are we really doing? We're thinking, what is that height up to the function? Well, it's 4 times x, right? Wherever I choose to take x, this height is 4 times that. The y value is 4 times the x value. Simple as that here. Okay, let's do it. Volume then will equal pi. Hey, what are the limits on our integral? Where should we start and stop? We're going to begin here. Well, that's at 0. We're going to stop here. Well, that's at 2. So we're going 0 to 2, 4x squared dx. And this will do it for us. So volume pi, let's simplify here. 16x squared dx. Okay. Well, we got another constant, right? We could pull that out. 16 pi integral x squared. Okay. Integrating, it's 1/3 x to the third. I'm going to say 16 pi over 3 x to the third, just to make that a little simpler. Evaluate from 0 to 2. And here's one trick. If your constant is maybe something like this, you don't have to write it for both terms. You could write that in front and then think 2 cubed minus 0 cubed, and it's like this is factored out. Makes it a little bit easier. And then from here, we can get our final answer. Let's see, that's going to be 8 minus 0. So 8 times the 16, 256 pi over 3 is our volume. Very cool. Very cool. Got it. Okay, again, like what's key here? A good drawing, a good, indicating the correct region, and then knowing how to draw your radius. Knowing how to draw your radius and then identifying what it's equal to, and you're in a really good position. Okay, let's do another one. Part B was y equals square root x, y equals 3, x equals 0. Again, about the x-axis. Okay, getting a little bit harder now. Let's see what this is all about. Again, highly recommend graph these somehow. Desmos is great. Maybe you can do it by hand. Square root, something like that. Y equals 3. It's going to be a horizontal line. It'll cross somewhere. X equals 0 is the y-axis. So what region are we talking about here? It's going to be this curved region right here. Okay. Looks good. How is it being revolved? X-axis again. It's spinning this way. Okay. Aha. All right. First question. Is this a disc or a washer? As this spins around, does it leave a gap? Yes, it does. This will be a washer. Now, you might think, well, but doesn't it come down and touch down here at the very bottom? So the hole doesn't go all the way through. That's correct. But for the rest of it, except for that one point, the rest of it, there is a gap as this thing spins around. So if there's a gap anywhere, even if it's not completely through, we still are going to use the washer. Okay, for the washer, we need an outer radius and we need an inner radius. What are those? Okay, so for both of them, I'll draw the outer radius first. We're going to begin on the axis again, right? And then go perpendicular away. And I'm going to go all the way to the outer edge of my region. So this right here is capital R of X. For the inner radius, same idea, but go to the inner part. Don't go across the region, just go up until right there. Okay, so that's a little R of X. Looking good. What are these going to be equal to? What is capital R of X equal? You think, well, if you're coming off the x-axis, it's the function. I mean, that's all it is. So here the function, it's hitting y equals 3. It turns out our outer radius for this setup is a constant. No matter where we take the outer radius, it's always exactly 3 units away from where we're rotating from. How about little r of x? Yeah, well, yep, you guessed it. It's square root x. This one will change, right? Down here at x equals 0, the inner radius is actually nothing. There is no inner radius. It's 0. But as we start moving along, the outer radius gets bigger. Okay. You know what? We also need to know where these intersect. We know the region will begin at 0, but where does the region stop? Where do those equal each other? Where does 3 equal square root x? And well, that's going to be at x equals 9. When the outer radius actually equals the inner radius. Okay. So here the volume, we're all set up. The volume will be pi integral from 0 to 9. Outer radius squared minus inner radius squared dx. Remember, it's always outer squared minus inner squared. Okay, we simplify that. It actually cleans up pretty well. 9 minus x. In this case, that's pretty good. Square root, right? And from this point, you know, we're kind of home free. That's going to be 9x minus 1/2 x squared from 0 to 9. So volume pi, let's see here. 9 times 9 minus 1/2 times 9 squared. And plugging in 0. Oh, plugging in 0 is nice. 0. So our answer, what are we going to get? 81 minus 81 over 2. Well, anything minus half of itself is the half again. So 81 minus 81 over 2 is 81 over 2. So this will be 81 pi over 2. There we go. It's all said and done. Okay, we got it. Right. Again, what's the hard part, right? Drawing it. Identifying the region, right? Take your time with this stuff. You want to get it right. And then drawing both the outer radius and the inner radius, followed up by figuring out what they're equal to. Very cool. Let's do, I bet we can do one more here. We're on a roll. This one is kind of like part B. So yes, good. We're going to use the same functions, but this time, you guessed it, it's time to go about the y-axis. Same region though as last time. What's it going to be like if we go about different axes? Okay, so we still have this region. But now we rotate this way. So it's spinning like that. And it would kind of look like a top, right? After it's done spinning. Okay. All right, first question. Is this a disc or a washer? It is a disc. It's going to be solid all the way through. The region is bordering that axis all the way. There's no gaps anywhere. Okay, sounds good. If we're rotating about the y-axis, let's think about that. when we were rotating about the x-axis, right, we thought about where we started and stopped horizontally. If you're rotating about the y-axis, you have to think about where you're starting and stopping vertically. What does that mean? For a vertical axis, we need to integrate with respect to y. Not too hard to remember for these methods. If you're integrating on a vertical axis, you got to switch you're not really changing perspective this time, but you got to integrate with respect to the other thing, because we got to say, hey, we're going to begin at 0 and we're going to move up the region. We're going to stop at 3. What does that mean for the radius? Okay, to draw the radius, start on the axis and then move perpendicular. So we got to move across this way. There's our radius. But hey, if we're doing this with respect to y, we need to think of this as r of y. All the functions are functions of y now. Oh boy, all right. What does that imply? Well, just like before, when we integrated with respect to y, we're going to have to rewrite any equations. Really, it's just going to be this one. Solve for x. Hey, if y equals the square root of x, what would x equal? Well, y squared, right? So we need to rethink of this curve as being x equals y squared. Okay, perfect. That will help us figure out r of y. What is r of y going to equal? Well, very much like in the last two, if you start on the y-axis and then you move out, you're really just thinking, right, what is the horizontal distance there? Well, the horizontal distance is described by x, and x is equal to y squared. So r of y will equal y squared. Now, if that seems kind of strange for a second, you can check yourself anytime you figure out a formula for one of your radii. Think about it like this. We're taking all of these little circles, all these little infinitely thin little volumes, moving up the y-axis. So the first little volume we take is here at 0. Now, the radius there is nothing, so there's no circle there, but okay. Then we'll take another one a little bit higher up and another one a little bit higher than that, right? All the infinitely many until we get all the way to the top. And we'll create our solid. So let's think, hey, when y equals 0, what radius do we see? You know, if we were to draw that 3D figure, well, the radius should be 0 right there. And it's true, if we take y equals 0 and we plug it in, we do get a radius of 0. What's the radius at the very top when y equals 3? The radius here is 9, right? We figured that out before. Well, if y equals 3, would that produce a radius of 9? Sure would. Y squared, 3 squared, would give us the 9. And it would be true for all these other values of y in between, all the infinitely many. If we take that y value and square it, that tells us how far the radius is at any given point. All right, we're ready to go. The volume here is pi. Our limits of integration are 0 to 3 going vertically. And then we're going to take our radius squared dy. Okay. Once we've made it this far, we're probably pretty much in the clear. We can just knock it out. Let's see, that's going to be pi over 5 y to the 5th, 0 to 3. pi over 5. Let's just say parentheses 3 to the 5th minus 0 to the 5th. What is 3 to the 5th? Let's see, 3 times 3 is 9, 27, 81, 243. 243 pi over 5. Not unusual. I mean, all these are going to have pi in the answer because of that pi in the front. We get these fractions. Okay, hey, we got it. 243 pi over 5. I don't know. I mean, I can't really visualize what that number is exactly, but or if that would make sense for this shape, but you know, that's what we got. All right, again, right, be careful with the region. If it's a vertical axis, if it's the y-axis, integrate with respect to y. Rethink any equation as x equals. Draw your radius like so. Here, if you're coming off an axis, you know it's just going to be the same as our function set equal to x. And there you have it. All right, let's stop here. We'll do the last couple of examples next.